Hey everyone, and welcome to this explainer. Look, if you're a high school student gearing up for that massive science exam, you are exactly where you need to be. We're going to take all those super dense textbook pages about matter and completely decode them for you. It'll be a clear, step-by-step journey that'll absolutely click. So get ready, because we are about to make the invisible world visible.
Okay, so here's our roadmap for today. First up, what is matter? Then we'll hit the 3 states of matter. Third, how matter changes state. Fourth is evaporation and everyday life. And we'll wrap the whole shebang up with some crucial revision notes and a quick quiz. Section 1. What is matter? The journey of the particle. Let's just establish a foundational truth right out of the gate. Everything we see, touch, and breathe is built from something much, much smaller. I mean, whether it's the chair you're sitting on or the air in your lungs, it all has mass and takes up space. But, how did we actually figure that out? It's kind of wild, but humans have been trying to make sense of this forever. Just look at the early Indian philosophers. They believed literally everything was made of the Panch Tattva, basically 5 elements: air, earth, fire, sky, and water. And the ancient Greeks, they actually landed on a super similar idea. But obviously, science evolved. Modern scientists threw out the philosophical elements and now classify matter strictly based on its physical properties and chemical nature.
Right, so now that we know what matter is, we've got to talk about the tiny particles making it up. These little guys have 3 main characteristics. 1, they have space between them. 2, they are constantly moving, so they possess kinetic energy. And 3, they attract each other. Now think of that attraction kind of like a human chain. In a solid, those particles are locked together super tight, basically like traditional bihu dancers locking arms from behind. Nobody's going anywhere. But in a liquid, that attraction is way weaker. It's more like a group of friends just loosely holding hands.
Section 2. 3 states of matter. Comparing forms.
So, moving from individual particles, let's look at how they group together to form the 3 physical states we interact with every single day. If you look at the solid state shown here, those particles are packed in so tightly there's practically 0 room to move. Then, check out the liquid. You can see there's just a little bit more breathing room there. And finally, the gas. I mean, look at that vast empty space between the particles. They are totally free to roam around and just bounce right off the walls of their container.
Let's translate those visual differences into actual facts you can use on your exam. A solid has a definite shape and it's rigid. Think of it like a completely packed school hallway right between classes. Everyone is just shoulder to shoulder stuck in a rigid shape. Now a liquid, that flows and takes the shape of its container. That's more like a flowing crowd of students pouring into the cafeteria. And a gas, highly compressible, with particles moving at totally random high speeds. Basically, imagine students running completely freely across a massive open gymnasium.
Section 3. How matter changes state. The effects of heat and pressure. Okay, we know the states, but the universe isn't just frozen in place, right? What actually happens to these forms of matter when we blast them with extreme heat or pressure? Let's walk through it step by step. Let's say you heat up a block of ice. You're applying thermal energy. As step 2 shows, that makes the kinetic energy of the particles shoot up so they start vibrating way faster. Eventually, in step 3, that energy gets so strong it literally breaks the forces of attraction holding them together. Finally, they abandon their fixed rigid positions and boom, the solid melts into a flowing liquid.
Exam alert. Pay really close attention to this next part because it is heavily tested. The latent heat of fusion. Latent literally means hidden. So when ice is melting, you can keep pumping heat into the beaker, but if you look at the thermometer, the temperature won't rise at all until every last bit of ice is gone. So, where did all that heat go? It went entirely into breaking those particle bonds. That hidden energy is your latent heat of fusion.
And you know what? The exact same principle applies when you boil a liquid into a gas. That's the latent heat of vaporization. Because of this extra hidden absorbed energy, the particles in hot steam actually hold way more energy than the particles in boiling water, even if they are both sitting at the exact same temperature of 100 degrees Celsius. Honestly, that's exactly why steam burns can be so unbelievably severe. This brings us to sublimation, which brilliantly illustrates one of the coolest mechanics in physics. Like, what if we just skipped the liquid phase altogether? Well, some substances, like camphor or dry ice, do exactly that. When they get hit with a specific change in temperature or pressure, they just bypass liquid completely and change straight from a solid into a gas. No liquid required.
So all of these processes link up to build this really neat interconnected cycle. Solid to liquid is fusion. Liquid to gas is vaporization. Gas to solid is sublimation. And of course, it goes in reverse too. Gas to liquid is condensation, and liquid back to solid is solidification. I'd highly recommend hitting pause right here and just memorizing this entire triangle for test day. Section 4. Evaporation and Everyday Life. Science in Action. All right, it is time to connect all these abstract microscopic theories back to the real world. We're going to see science in action with evaporation. Now, unlike boiling, which happens to the whole bulk of the liquid, evaporation only happens right at the surface, and it can happen at any temperature below the boiling point. The crucial thing to remember is that 4 main factors speed it up: increasing the surface area, bumping up the temperature, lowering the humidity, and increasing the wind speed. This is exactly why if you spread out your wet clothes on a sunny, super windy day, they dry way faster than if you just left them crumpled up in some damp room.
And here's a really cool everyday connection. Evaporation actually causes cooling. When the surface particles of a liquid finally gain enough energy to escape into the air as a vapor, they have to steal that energy from their immediate surroundings to do it. Have you ever wondered why sweating cools you down after a really intense gym class? It's literally this. As your sweat evaporates, it absorbs your body heat to make that state change, leaving your skin feeling so much cooler.
Section 5. Revision Notes and Quiz. Test your knowledge.
All right, rally your energy. We are in the final stretch. Time to lock down the most important facts from this explainer so you can walk into that exam feeling totally bulletproof. Definitely pause and write these down. If you remember nothing else, these 3 facts are the absolute bedrock of this chapter. Number 1, matter is made of small, constantly moving particles. Number 2, the states of matter are interconvertible by just changing the temperature or pressure. And number 3, evaporation is a surface phenomenon that absolutely causes cooling. Next up is a super essential glossary of measurable quantities. Trust me, teachers absolutely love dropping standard SI units into tricky multiple choice questions. So remember, temperature's SI unit is the Kelvin, guys, not Celsius. Mass is the kilogram, weight is measured in newtons, and pressure is measured in pascals. Keep this table handy for your final review sessions. Okay, let's put it to the test. Quiz 1. Why does the smell of hot, sizzling food reach you from several meters away, but for cold food you have to get right up close to smell it? Think about it. Got it? It's because higher temperatures increase the kinetic energy of the particles. Since they're moving way faster, the aroma particles from that hot food diffuse through the air so much more rapidly than the cold ones.
Let's try quiz 2. What is the scientific term for the amount of heat energy required to change 1 kilogram of a solid into a liquid at atmospheric pressure exactly at its melting point? I'll give you a second. Remember our big exam alert from earlier? It's the latent heat of fusion, that hidden energy used entirely to break those bonds of attraction.
Last one, quiz 3. How does an increase in humidity in the air affect the rate of evaporation of water? Think about the air kind of like a sponge. Because the humid air already holds a ton of water vapor, it can't take on much more. So when humidity goes up, the rate of evaporation actually goes down.
You guys crushed it today. But as we wrap up, I want to leave you with one final, totally mind-bending thought. If literally everything around us, the screen you're looking at, the chair you're sitting on, even your own hands, is mostly empty space between microscopic, moving particles, why does the world feel so solid when we touch it? Keep pondering that massive physics paradox long after this explainer ends. Good luck on your exams. You're going to do